think you are already using the electron microscope, right? It's only for EDS, EPSB or imaging also, or what? May I know your area of research and where you are using, so that accordingly I can instead of starting from the complete microscopy. So it's a demonstration for STEM detector only today. So all the other parts I think we covered during our last visit. But today we will discuss more on the scanning transmission electron microscope. Hope you have used the STEM as well. STEM for structural information, particles, very narrow particles, right? So no, I want to know whether you are already using it or for your research purpose, or is it the first time you are submitting samples?
Sir, I am first time here.
First time?
Yes, sir.
Area of research?
Sir, my area of research is nanophosphor materials. Nanophosphor materials and perovskite materials, yes, sir.
For which application?
Sir, I am currently I am doing in the area of forensic science and latent fingerprint detection. Latent fingerprint detection. Yes, sir.
Yeah, forensic also there are lots of applications.
Yes, sir.
SEM. Even we have starting from the diatom, water diatom. People take suicide, whether it is a suicide or whether it is somebody pushed. So looking at the diatoms present in his body, the density of diatoms in the water, the presence of those diatoms in SEM, we will study through SEM only, and then we will identify whether it is through somebody pushed him or it's a suicide. So for such applications also you can use it. In accidents, in paint thickness, different multiple paint layers, because when it touches some other body, right? So even forensic application. And there is a dedicated special software, non-residual GSR, short residual software. So where you can identify the person who is surrounded, like whether he is present in that particular murder. So such applications, there are so many. If you take it forensic side, the application is completely different. If anybody working on the soft samples, which sample? Animal, so biological samples particularly. So normally people find difficulty using the electron microscopy, right? That's completely, the samples are soft, the samples are beam sensitive, the samples contain some moisture, samples, if you bombard it with higher kV, then the beam induced effects will be up there. So your area of interest, your region of interest, your particularly feature of interest, you are not able to do that, right? So you have a different ways to handle such samples. Biological samples, see, I just categorize your sample as a bio sample. So biological sample, if you want to handle in high vacuum, you cannot do that. So there is three ways normally you can do. One is you have to coat the sample with the gold or a conducting material, which others is already doing with these sort of things. So when you have a non-conducting surface, for example, this is your non-conducting surface, the biological sample, insulation sample, right? When you pour electrons on this, so because of this, definitely the electrons cannot conduct, because this is a non-conducting nature. Then it will form a negative cloud on the surface. When an electron beam interacts, whatever the secondary electrons are coming, which cannot reach the detector, right? So in such case, the idea is to remove this negative cloud, because this sample is not allowing it to pass through. So what is the way is, either you have to coat with the conducting material, which is gold, the first method. If you want to see the sample in its nature, in its native condition, instead of making their conducting, if you want to do it, you have a variable pressure technique where you introduce some gas molecules, and then that gas molecules will interact with the electron beam, and then it forms an ions. Once ions, because of heavy nature, will sit again in the sample surface. Then again it neutralizes, and you can use you can visualize, you can image the biological. The third way is FESM, particularly the Gemini column, what is from size, uniqueness of sizes, you can do low kV imaging. That means you are not bombarding with a higher kV. You will bombard with hardly 100 volts, hardly 1 kV, 500 volts. But even the system is capable of picking the high resolution images. So 1 kV image also you can capture at very high resolution. System capability, if you see, the system can resolve sub-nanometer also. So I discussed about three ways of handling the non-conducting sample. Gold coating, second one is a variable pressure technique, third one is the low kV performance, right? So low kV performance, not air to capture. So non-conducting substance. Another way to handle, another way to handle these things. For example, if your sample, if you take it to a vacuum, then it will lose its surface property. Then you have to do it in a liquid buffer solution only. If sometimes you want to do that in its native condition without losing the surface properties. All I am talking about very sensitive surfaces. I am not talking about the micron range or a bigger one where we can easily image with the normal conditions. If you want to do that, even system comes with the cooling stage. You can freeze the sample up to certain temperature. There are different cooling stages can allow you to do up to -50. The cryo stage can go up to -189 because here we are using only Peltier technique, but there we use a liquid nitrogen. So that's a separate technique, but definitely biological samples or those who are working in tissue like to handle the samples in a different way. If you have a liquid samples also, don't confuse that the SEM can give the analysis for liquids also. If you freeze those samples through this cryo or a cooling stage, even you can visualize the solid particles inside that liquid material. That's a way to handle different difficult samples. All other metals, thin films, coatings, fracture analysis, if you are working on a chemical route where you synthesize some materials, precipitates, or these are all very easy, direct, straightforward, and you can do. The challenge will come only when you do with the non-conducting samples, beam sensitive samples, biological samples, moisture contained samples. So in that, even the systems are capable of handling 100 volts. I am talking about the system capability is 30 kV. But images at 100 volts of 100, you see the scale bar is 100 nanometer. So that means the distance between or the pores, these are all even less than few tens of nanometers. So such high resolution images also very much possible with these FESMs. Okay. Now the main the agenda for today is the discussing about the STEM. Even in electron microscopy, most of the time you analyze the surface information, right? So because you are picking up the electrons which are coming out from the surface after electron beam interaction with the sample. So there are secondary electrons, backscattered electrons. Similarly, even we can pick up a transmitted signal as well. So in TEM, what you do in TEM, the sample is so thin, and your source in between there is a sample, and your detector is below the sample. Similarly, in SEM also, people call poor man's STEM, because TEM is getting a TEM slot or TEM itself is a very expensive tool. Here the only limitation what you have is only this can go up to 30 kV only, but whereas TEM, I think you have a bio TEM can go up to 120, and materials TEM people have a 200 kV, and HR TEM people have 300 kV also. Yes. But the only limitation here is the kV. If you prepare the sample thin enough, so that even you can get a transmitted signal. The system is designed, the sample holder is designed in such a way that it again forms the same structure of your TEM. So from here the electron beam will come out, and then we will introduce the TEM sample holder, which looks like this. At a time you can load 12 samples, and then below that you can bring the STEM detector. Our STEM detector again a segmented STEM detector, where you can get the complete different informations, because if you pick up the complete transmitted signal without any interactions or deviations, the bright field imaging you capture, or if there is any collisions, and then if you pick up at a particular angle, you have a dark field imaging also, angular dark field also, high angle dark field, which is almost common in your TEM imaging. So all such things are available even with this step, but the only limitation is the 30 kV imaging. Apart from that, the sample also has to be prepared in such a way like you submit the sample to TEM. The main important here is all samples you cannot prepare, you cannot pay for TEM analysis, right? To analyze whether the sample is prepared well or not, whether it is thin, then you can image those things in here, and you can, out of 10 samples, 1 or 2 samples you can proceed for further TEM imaging or STEM imaging. Or if you are looking for some nanoparticle images which are less than the 1 or 2 nanometer, even those images also you can be captured few images where so here the particle size, if you see this scale bar itself is 20 nanometer. So the distance between these two particles is when we use there is a software to measure the resolution of the particular image. Yeah. So it will measure the different edges between these particles and through the statistical method it will give you the resolution, which is 0.5 nanometer even resolved in this. So where I am coming is the samples or the feature size which you are looking for, few tens of nanometers also can be resolved in the field emission scanning electron microscopy, low kV and high kV. No need for all the samples, no need to go for TEM. But TEM has its own advantages. Definitely the structural information, if you want, all those things you cannot get it. But most of the nanoparticles, or if you have the biological samples, we can quickly base and get the transparency. One more development in this, as of now you don't have, but so even another advantage with the TEM analysis is like tomography. People do the complete 3D information. Even we designed a detector in such a way that the sample, how you are able to do the tomography, once you have the surface information and if you tilt plus or minus 70 degrees, normally in TEM holder, if you know, the TEM holder will go plus or minus 70 degrees, and in all that angles the system will collect the slice information. Later through the algorithm it will stitch and give you the complete 3D tomography. What it means is the complete 3D volume information, how exactly inside it is. But the sample size is very limited, 3 mm. Similarly here also, our sample holder will go plus or minus 60 degrees. This is not the sample holder. There is an advanced sample holder where you can pick up the complete plus or minus 60 degree information, and then using an Atlas advanced software, you can stitch it and you can get the complete 3D volume also. So that's all normally in the STEM imaging we do. All other detectors, I think you know, the SC, BSc, Lens SC, Lens BSc, what exactly the difference between those image contrast and all those things. I hope you already covered it during the last slide. Any questions on
Sir, what about powder samples?
Powder sample, if you nano powders, if you
Yes,
you
sir.
have to do it on a drop caster. First disperse those things in a buffer where the particle properties won't change, and then on a 3M grid where the carbon supported 3M grids will be there. So on that you have to drop cast, and similarly the holder which is this one. This is the holder where the sample will tilt plus or minus 60 degrees and pick up the tomography information also. But for TEM, for your samples, yeah, the sample holders are same, the samples are same, 3mm grid only. Carbon supported 3M grid, if you take and drop cast on that and drive, you can do the holders. But again, the question is like when you prepare, you should be very thin. Otherwise, 25 kV, 30 kV signal has to transmit to the system.
Sir, if our sample is amorphous, then what will the approach of record these images?
No, whether it is a crystalline, it's all matters with your EBSD, because when you go for the crystallography information, but for imaging part it doesn't matter. Like it is only thing is it comes under conductivity sample or non-conducting sample, how to handle with the different parameters. Whether it is amorphous, whether it is a crystalline in nature. For imaging part on the surface, it's something different. Only when you go for EBSD, where you are going to read the crystallography information or the electron channeling contrast. So in such a different application, that nature will.
So can we provide substrates as well? I mean, this type of substrate we can give.
You mean to say the sample holder?
No, sir. If I am spreading the sample on any substrate like F2 or I2, can we?
Which sort of thing are you working on? Anything?
Yes, actually TM-based material. I want to want TM-based material, and I need to make a thin film on the substrate to make a device. So which type of?
So for this sort of system, if you prepare it on a good conducting material, that is easy. And always where ITO still okay, but the glass is non-conducting, but the coating what you do is allows. But when you have too much of interaction volume, Again, the cross section, how you will do the cross section. For example, this is your sample, and if you coat the sample like this, so you have to prepare a cross section like this, and you have to image the multi layers here, right? So, but one part of that sample, the base is glass. Glass is completely non-conductive. Okay. So, if you have any silicon wafer is also the very flat with the nano roughness, right? So even your thin film surface properties also, it's all depend how adhesive, what you are looking for. If you are later going for a indentation and identifying the mechanical properties, that I don't know. But if you prepare on a good conducting substrate or a silicon wafer, quartz is also okay. You can prepare it and then prepare. Most of the time, the cross section with the thin film thickness is in nano scale, then cross-sectional preparation is very important, because once you coat like this, and if you say I am cutting with a diamond cutter, your 10 nanometer, 20 nanometer, because of the external stress which you apply during the breakage or this thing, will bend your the top layers. We have so many samples, so better you cut it with the diamond cutter or whatever the way you handle, and then do the polishing of that surface, so that your whatever the external stress which bends your sample or a thin film, that became flat, and then right, this diamond paste and all those things, to the different particle diamond paste, polish it properly, try to remove this thing. Instead of, before that you have to make a mold of that sample, then it is easy. I'll show you